So this is about how to derive the unit circle. So first you want to start by drawing your quadrant lines. And then, this is 1, 0. You know that this is 0, 1. And then this is quadrant 2, and we know that this is negative x component. This has a negative x component. If you go down here, this has a negative y component for both quadrants 3 and 4. So we know there's 3 lines that reside in every quadrant. Now to remember this, we just kind of have to remember 30, 45, and 60. And it just starts off with this pattern of adding 35 from 0 degrees to adding 15 to adding 15 in every single quadrant. And this also may be in your coordinate system, could be in radians. So if you want to think of it in radians, pi equals 180 degrees. So from here you can do some simple division, and for example, 60 degrees equals pi over 3. So that would be pi over 3 radians. That's just what it is in radians. I'll go through that here in a second, but I want to get through this. So from here, the main thing we want to know, the most important part of this would be these x and y values associated with every single angle. So you have to remember that every single one of these is divided by 2 for every single component, for every single degree, unless it's one of these main components like 0 degrees or 0 degrees, 90 degrees, 180 degrees, or 270 degrees. But all these other ones will be divided by 2. And then this is really the way to go about it. So I know square root of 3, square root of 2, and square root of 1 are the values in here, are the values that we will use. So for this first angle, we have 30 degrees. So we want to think, we're looking for the x component right here. We want to think we can compare this angle 30 degrees to these other angles. We can be like, when we're closer to the closer we are to 0 degrees, we know that this x component is longer. So from that, we know that this first one is going to be the square root of 3. Since the square root of 3 is our largest value we have down here that we know plugs into this data. And then from there, we can just follow the pattern, and we know 45 is square root of 2 and square root of 1. Or you could just write 1 there, but I'll just leave it at square root of 1 just for the pattern. And then you could just remember that the y is the opposite, because for this to be a balanced triangle, this kind of has to be the opposite. But also you could just think, this angle here, this side here, is less, this y component is smaller here than it is going to be up here at 90 degrees. So we know the further away this angle is away from 90 degrees, the smaller that y component is going to be. So we can just remember that the y component there is the smallest value, which would be 1, and then it just gets larger and larger. Square root of 3. And that makes sense because we know at the top is where the y value gains its largest value, because that is the top of the circle, the unit circle. Hence why we use a 1 there and everything. And then if we just go over here, it's the same thing. It's just the x component is negative. but I do think this pattern is important. So for this pattern, we just need to remember three angles in every quadrant, and then we add 30 for the first one. So 90 plus 30, 120. 120 plus 15, 135. Add 15 more, we get 150. These are all degrees. That's a pattern to find the angles, and then we can use that same logic we applied over here in the first quadrant to over here. So we know that 120 degrees, we know that the y is large, so we know that's square root of 3 over 2 for the y component. And then for the x, we know it's negative because it's in quadrant 2. And then we know that we're using the square root of 1 over 2 because this x value associated with this angle is very close to the center line, to the y-axis. Yeah, so I'll do some, so I think it's pretty self-explanatory from there. You just keep following the patterns using these values, and you will be able to derive the whole everything. Now, why is this important? This is important because we can take the cosine and sine. These are very common angles as well. And take the cosine and sine of these angles, and we use this in a lot of classes, calculus, physics, all these things that are just studying physical objects and, everything else. There was something else I wanted to talk about. Really, when you go to change these, so like if you have, let's say we want to convert 270 degrees to radians, you can just go and multiply the whole thing by pi over 180. You get 270 over 180, and this is pi. I'm just going to slap that pi on the front of this fraction. Just get rid of those zeros. 27 over 18. We'll divide them both by 9. And you get 3/2 pi. This is just how you just turn any of these degrees, any of these angles to radians by multiplying them by pi over 180 and then simplifying the fraction. But yeah, this is used in a lot of classes, pre-calculus, calculus, physics, a lot of engineering courses, a lot of physics. Yeah, I'll do some cosine and sine. I'll do some trigonometry right here. So if we want to take the sine of an angle, we'll take the sine of 30 degrees. So we can just do this from memory of the unit circle. So we know from the unit circle we have a triangle like this is the first quadrant drawn. This is the 30 degrees. We know looks about like that. So when we're looking for the sine of this angle, we can remember the SOHCAHTOA. So we know sine is opposite over hypotenuse. So it's this right here. It's this leg. And then when we associate that leg with the unit circle, we know that's just the y component. So the sine of 30, just from memory, we can remember that the y component is small at the sine of 30. So we know it's the square root of 1 over 2. We can do this, and then the main